Good morning, good afternoon, good evening, whatever the case may be. My talk today concerns how this unique challenge of transitioning to a net zero greenhouse gas emission world society should change how we select and evaluate public policies to accomplish the transition. And the reason for that is this process takes a long time, it's complex, and it involves deep uncertainty. I'd like to begin with an anecdote. A Harvard neuroscientist named Professor Lichtman, who was mapping the estimated 2 exabytes of data required to describe the interconnections of the human brain, one brain, was asked if scientists would ever understand the human brain. No, he said. Do you understand New York City? Too much is going on. There's too much complexity. We've undertaken to urgently transform a holistic global system that's interconnected with every aspect of human society and the environment. No, we don't understand the transition to a net zero greenhouse gas world. I can't say it better than the quote on this slide. A multi-decade evolution of technologies, socioeconomic conditions, and politics, such as that associated with the transition to a net zero energy system, is characterized by deep uncertainty. Now, scientists have long recognized that it's important to include uncertainty in the modeling and analysis and reporting of results about climate change. And decision science has also developed methods for coping with uncertainty in rational decision making. And these methods have been used and adapted for deep decarbonization, and I'll say a little bit about them later. But too little attention has been paid to how deep uncertainty should change the ways we formulate, select, and evaluate policy strategies for achieving decarbonization. Deep uncertainty is defined as a situation in which experts and decision makers cannot agree on the probabilities of relevant influencing factors, the appropriate models for representing the phenomenon, and perhaps even how to value the possible outcomes. I think that well describes the problem of transitioning to a net zero greenhouse gas society. Deep decarbonization has to address this problem of deep uncertainty head on. As Rosenblum put it et al. In their seminal article in the Proceedings of the National Academy of Sciences, quote, in order to address the urgency of climate change and to achieve deep decarbonization, climate policy responses need to move beyond market failure reasoning and focus on fundamental changes in existing socio-technical systems such as energy, mobility, food, and industrial production. We have to do this because the time constants for change are so long. There are expected vehicle lifetimes exceeding 15 years. Redesigning vehicles takes time. Tooling for that redesign takes time. In the meantime, the technology is changing. And we also have many things we don't understand about how well the market, the consumers and firms will accept these novel technologies and adapt to them and work efficiently with them. And this transformation is going to be made in a future that has a lot of uncertainties of its own. Technologies will change. Markets and preferences will change, public attitudes and policies, and the world economy will change, and it will even respond to and adapt to the deep decarbonization and the changes that are being made to achieve it. So this changes the policy-making process. It changes also the criteria for evaluating policy. Uncertainties take many forms, including the famous unknown unknowns. But I think it's useful to categorize the uncertainties that are going to most prominently affect deep decarbonization. And I've come up with 5 different kinds. First, the most obvious is technological. Technology will change. Technology is essential, and technology change is essential to accomplishing this. Its cost, performance, and the attributes of the technologies will change over time, and technologies we don't know about will be created. There will be behavioral change. This affects the acceptance of the technologies, the demand for the services that energy and other things provide, and there will be adaptation and changes in human behavior. There'll be political changes. governance. How do we govern this transition process? A lot of progress has been made, but it's still a very challenging undertaking. Institutions will need to be created. New institutions have been. These are not all that we will need to accomplish this. And then there's the very important question of public support. The public has to be behind this, and really firmly so, for decades if we're going to accomplish it. Then obvious macroeconomic changes, population, demographics, economic growth, and how the market responds to the broad changes that will occur, such as near elimination of fossil fuels. And then there are geophysical uncertainties about climate change itself, but also uncertainties about the resources that will be required for the new technologies that will be used. And we will, I think, at least adopt some form of geoengineering, and how that will work very much remains to be seen. So all of these different uncertainties are mediated by markets, by prices, and by governments and policies and society, and result in a transforming of the system. And one of the outputs of that is the deep decarbonization we are most interested in. And we have to keep monitoring that, keep looking at that situation, see how we're doing, what's working, what's not working, adapt, and then keep carrying on. In the following slides, I'm going to give an example of each of these just for illustrative purposes, just one example of many, many that one could come up with. This slide illustrates that despite the amazing progress we've made in battery technology and fuel cell electric vehicle technology over the past years, there's still a way to go. 10 years ago, at $1,000 a kilowatt hour, the batteries for a modern battery electric vehicle that gets a 250-mile range would cost about $65,000. Today, that's much, much closer to the cost of internal combustion engine powertrain at something like $6,000. So that's an amazing improvement, but it's still not exactly where we need to get to in terms of the cost of the batteries and in terms of the charging time for the batteries, and so on. So this creates still remaining uncertainty about how we should proceed. Should we put all our eggs in the basket of battery electric vehicles and push hard on that, or do we need also to continue pursuing fuel cell electric vehicles and a hydrogen-powered system? So this is even more relevant, I think, for freight transportation than it is today for passenger transportation. On the left-hand side, we see a tool, a decision tree, that's used in engineering options analysis, one of the ways of coping with uncertainty in technological progress. And the percentage reductions in greenhouse gas emissions are from the study cited by the National Academy of Sciences, but the other numbers are just made up by me for illustrative purposes. This particular example shows how the best option is to pursue efficiency and battery electric vehicles and fuel cell electric vehicles, because it gives the greatest chance of large reductions in greenhouse gas emissions, even though it costs more. But in fact, we really don't know the probabilities of success, and we don't know the total costs either. So uncertainty remains, and is substantial. This next slide is intended to illustrate behavioral uncertainty. Here we have projections of the market share of battery electric vehicles out to 2050 by various organizations. You can see they span a range from about 10% of the market, or even less, to almost 100% of the market. Obviously, these projections taken together don't convey much information. In reality, the speed and extent to which key zero-emission technologies like electric vehicles will replace fossil fuel technologies depends strongly on customers' willingness to accept novel technologies and potentially new paradigms of service provision and business models. The central premise of the theory of diffusion of innovations is that it is a social collective process, not solely a rational economic decision by fully informed utility maximizing individuals. But policy evaluation is usually based on the economic theory of rational consumers and producers, and may reach wrong conclusions about how long this will take and what is necessary to efficiently and effectively accomplish the transition. This next slide just shows the case of hybrid electric vehicles in the US economy. Hybrid electric vehicles have been in the market for 2 decades by 2019. They offer a 50% improvement in fuel economy, a 1/3 reduction in greenhouse gas emissions, and that the prices that they were selling for in 2019 had a payback period of 3.5 years, which is extremely good, obviously. But they had less than a 3% market share. They're doing a little better now. Last year, about 5%, and projections for this year about 9%, due to reestablishing fuel economy standards and some increase in gasoline prices as well. But this highlights a major behavioral uncertainty. Despite the importance of energy efficiency to deep decarbonization, we still don't understand why markets seem to underprovide it. There's an ongoing debate. The example here is this hybrid vehicles, but it goes across the entire economy and affects everything from air conditioners to industrial processes. The next slide is intended to represent political uncertainty, although coming from the United States, that seems hardly necessary. I mean, our commitment to effectively addressing climate change as a member of the international community essentially took a 180-degree turn in the last election based on a few tens of thousands of votes in a handful of states. So the political uncertainty is very substantial. Although a majority of Americans believe the government should do more to mitigate climate change, only about half of the public believe that human activity contributed to climate change a great deal. This issue was made politically divisive by deliberately disseminating misinformation and false attacks of trustworthiness of scientific and government institutions. And unfortunately, it worked remarkably well. So the point is that the ability to implement and maintain energy transition policies depends critically on their acceptance and support by the public, by businesses, and other interested parties. We're clearly in a much better position now than we were 2 years ago, but still, that seems fragile and uncertain. The main point is that public policy should pay more attention to building and maintaining a strong public consensus in favor of deep decarbonization. That should be step one, really. It also means the choices among policy options should depend not only on their economic efficiency, or especially their theoretical economic efficiency, but also on the ability to gain and hold public support. This slide here illustrates a policy that's been in effect in the United States for almost 40 years, almost 50 years, 45 years, the fuel economy and greenhouse gas emission standards. And this policy has garnered overwhelming public support across the political spectrum. As you see, those supporting it are 66% of Republicans and 90% of Democrats. Those opposing it are a very small minority in the United States. Why is this policy so effective? Well, research on what makes policies acceptable to the public have come to the conclusion that there are at least 5 major aspects of policies that favor public acceptance. One is to put the burden of compliance not on the individual, but on firms, businesses, government, and so on. Of course, effectiveness and cost effectiveness matter, but so does equity. If people believe that the policy is fair to all, it's much more likely to gain public support. This public support over a sustained period of time is essential to effectively achieving deep decarbonization. This next slide is intended to illustrate one aspect of macroeconomic uncertainty. The fact that macroeconomic evolution is an emergent phenomenon creates a whole realm of uncertainties. Energy modelers assume an array of futures based on different assumptions about economic population growth, availability of natural resources, income distribution, productivity, technological change, policies, and other factors. But even the wide range of existing scenarios is likely to miss important, high impact, low probability events. The example here is just one. It's the uncertainty about the prices of future fossil fuels. And in particular, the possibility that deep decarbonization will result in very low prices for fossil energy sources, possibly making the transition to low carbon energy sources appear costly. Will people think in terms of, well, if we hadn't done this, fossil fuel would be a lot more expensive? Or will people think, well, fossil fuel is very cheap, why shouldn't we just use it? This decarbonization is very expensive. So this is based on, you see the history of oil prices in the world, which is very erratic. And you see in the solid lines on the right, future projections by the U.S. Energy Information Administration. And then my own estimates based on a simple supply-demand model and elasticities, price elasticities of what could happen if the world were to reduce petroleum demand by just 80% by 2050. And those prices are down in the range of $5 to $20, whereas the projections by the EIA range from about $40 to $180. How to prepare for and cope with very low fossil fuel prices should be an important aspect of policy formulation for the decarbonization transition. This final slide in the uncertainty series is just to illustrate geophysical uncertainty by uncertainty about what the climate impacts of greenhouse gas emissions will actually be. And there's a lot of uncertainty. For example, sea level, according to the recent IPCC 1.5 degrees centigrade report, could rise by half a meter to a meter by 2100, with 2300, 2 to 7 meters, but 15 meters is possible. So these are very different outcomes with very different implications for the world. And that's just one example. It goes on and on. How fast will the ice sheets melt? How much drought and where will it occur? How severe will the temperature changes be in extreme weather events and so on? But there's also uncertainty about more things. We need now reliance on lithium and rare earth metals rather than more petroleum and natural gas and so on. There are at least 5 methods that have been developed for coping with uncertainty and planning for deep decarbonization. These include robust decision-making, engineering options analysis, information gap decision theory, dynamic adaptive planning, and dynamic adaptive policy pathways. All of these methods share the following 5 principles. 1, clearly articulate uncertainties. Explicitly consider alternative courses of action and their vulnerabilities. The emphasis shifts from economic efficiency to robustness, durability, which depends on equity, as I pointed out earlier, and achieving objectives under a wide range of contingencies rather than optimality. Also, continuous monitoring of successes, failures, threats, and opportunities, and finally, adapting in response to that to change the policies to be more effective. All of this means we not only need different processes for formulating policies and strategies, but also deep uncertainty changes the criteria by which we should judge policies. It broadens the criteria to give greater weight to robustness, adaptability, durability, and equitability, and it magnifies the importance of transformational effects, system-wide interdependencies, positive feedbacks, and potential tipping points. Deep uncertainty is a fundamental aspect of the transition to a net zero greenhouse gas society. It's one that makes the problem unique and one that we need to respond to in the way we formulate and carry out policies. For your attention, and good luck with all your deliberations.